Okay, so hi everybody. So let's see. So let me open the chat in case. Okay. So so today is the last lecture of linear algebra for the differential equations part of the course. Oh, by the way, so if, I think somebody has their mic on who's maybe not talking, so please mute your mic. You're not saying something. So okay, so well, I hope everybody enjoyed the midterm and everything should be fresh in your mind. So we're gonna now combine some things from chapter 5 and 6 in a really interesting way. So what's the high level idea here? Or what's, just a second, I think somebody is still unmuted. So, okay. Yeah, I just muted everybody. Okay, good. So, okay, so what have we done so far in no, there was no lecture the day of the midterm. So what have we done so far? I'm sorry, in chapter 5. Well, we talked about how if you have a square matrix, an n-by-n matrix, then sometimes if it has enough eigenvectors, if it has a basis of eigenvectors, you can diagonalize it, right? So you can turn any square matrix into a diagonal matrix. And this is something that's much simpler to work with. And, you know, we saw that diagonalization had many applications. But this has some pretty important shortcomings. So one is that not every matrix is diagonalizable. And it's not even easy to check when a matrix is diagonalizable. You pretty much have to compute the eigenvectors and see if there are enough of them. Another, maybe more minor point is that sometimes you have to use complex numbers. So there are some matrices that you can't diagonalize them with real numbers, but you can with complex numbers. But this is also maybe a little annoying depending on your applications, depending on your application. And the third point, which is really not a shortcoming, but just a feature of the setup, is that it doesn't make sense for rectangular matrices, right? So even the eigenvector equation, right, ax equals lambda x, this equation doesn't even make sense if the matrix is not square, because then, you know, the domain and codomain have different, are different, and so such an equation can never make sense. And so what we're going to do today is we're going to remedy the first 2 points for symmetric matrices. So we're going to show, or we're going to at least say that this doesn't happen for symmetric matrices. I'll say what that is in a moment. And then in the second half of the lecture, we'll introduce something that's not quite as good as diagonalization, but something that allows you to represent rectangular matrices as some sort of diagonal matrices. And this is the singular value decomposition. So that's today's lecture. So let me start talking about symmetric matrices. So so here's a definition. A matrix, a square matrix, A is symmetric if it's equal to its transpose. Okay, so for example, this matrix is symmetric. Okay. So symmetry is a property that's, okay, there's a transpose in it, so it somehow should be related to chapter 6 in some way. And it's not clear what, if anything, symmetry has to do with eigenvalues. But there is one, let me introduce one definition. So we've defined we've defined what it means for a matrix to be diagonalizable. We'll say matrix A is orthogonally diagonalizable if A is equal to PDP inverse for some orthogonal matrix P. Okay, so this is a stronger condition than being diagonalizable, because to be diagonalizable, you just need an invertible matrix P. And remember that an orthogonal matrix P is a matrix with the property that P inverse equals P transpose. So being orthogonally diagonalizable actually means you're equal to PDP transpose for the orthogonal matrix, right? And what this means is, well, you know, since the matrix, whenever you can write a matrix as PDP inverse, the columns of P are the eigenvectors. What this means is there's an orthonormal basis of eigenvectors. Okay, so these are all different ways of saying the same thing. There's a stronger condition than being diagonalizable. Okay, so one easy observation is that if a matrix is orthogonally diagonalizable, then it's symmetric. Okay, so this is one relationship between these two definitions. And let me now prove this. Here's an easy. If A is if A is orthogonally diagonalizable, then it's symmetric, so it's equal to its transpose. And this has sort of a very easy one-line proof, which I will just do. Well, okay, what's A transpose? Well, A is orthogonally diagonalizable, right? So that means A is equal to some PDP transpose. And so A transpose is PDP transpose, right? So I'm using here that A is PDP transpose. But okay, how does transpose work? Well, you know, the transpose of a product is a product of the transposes with the order reversed. So this is P transpose transpose, D transpose, P transpose. But this is diagonal. So diagonal matrix is equal to its transpose. And transpose transpose is the same as doing nothing. So this is just P transpose, which is this has sort of a trivial fact. So the amazing thing, which is a very deep fact, is something that's called the spectral theorem. What the spectral theorem says is that the converse of this is true. So this is a highly non-obvious fact. Here's what it says. If A is real and symmetric, so all matrices are, I've defined symmetric for real matrices. Then two things happen. One, all the eigenvalues of A are real. Okay. And A is orthogonally diagonalizable. Okay, so again, what that means is there is an orthonormal basis of eigenvectors. So this is even stronger than being linearly independent, right? Because being an orthonormal basis is the strongest version of linear independence. Okay, so I mean, concretely, in terms of equations, there are some, I mean, okay, together these 2 points imply there are some n real numbers and some n vectors, also real, orthonormal, such that AVI equals lambda VI. Okay. So what this is saying is that none of these bad 2 things that can happen in general on the previous page happen for symmetric matrices, right? So on the previous page, I was complaining that these 2 things can happen. That sometimes matrices aren't diagonalizable, sometimes you need complex numbers. And what we just proved is that, well, this never happens for symmetry. And this should be kind of surprising because symmetry seems like a stupid property a priori, right? The matrix is equal to transpose. Why should that say something about eigenvalues, and which are come from solving the characteristic equation and so on? We won't prove this. Okay, but I will prove a tiny piece of it just to give you a hint of why symmetry comes in. I'm sorry, the V's are n. Thank you. My bad. Okay. So that's the statement of the spectral theorem. Are there any questions about the statement before I tell you a piece of a small proof of it? Okay. So let me now prove a small piece of it. I'll just call this a lemma. Well, okay, let's not call it a lemma. Let's just call it a part of the theorem. So one of the things that implies is that if A is equal to A transpose, and you have two eigenvectors of A with different eigenvalues, we have AV equals lambda V, and A, let's say W equals some mu W. Both are not 0. So they're both eigenvectors. And these eigenvalues are not equal to mu. Okay, so in words, this is just saying these are eigenvectors with distinct eigenvalues. So if it's symmetric and you have these 2 eigenvectors, then they have to be orthogonal. Then V is orthogonal to both. And this I will actually prove. And this is one of the pieces that goes into this theorem, right? So here we have to prove the eigenvalues are real. We have to prove, well, the hard part of this theorem is proving that for every eigenspace, that geometric multiplicity is the algebraic multiplicity. But there is this, orthogonality that's there too, and we can actually we can prove that whenever there are eigenvectors, they're going to be orthogonal. Okay, so let's prove this. Okay, so what's the proof? Well, let's write the eigenvector equation. AV equals lambda V. Okay, that's true. Let's now do something a little sneaky. Let's multiply this by W transpose on the other side. We can do that, right? Okay. So this is just equal to lambda times W transpose V, because that's how scalar multiplication commutes with this dot product. Okay. On the other hand, I'm now going to do something a little sneaky. I'm going to view this as being this vector times V, right? And what is this? Well, this is really A transpose W, the whole transpose, times V. So this is the key step, right? And that's how transpose work, right? AB transpose is equal to B transpose A transpose. Okay, so this is just comes from some fact about transpose. But now I'm going to use symmetry. This is the key step. Symmetry means A transpose is equal to A. So this must be equal to AW transpose V. Okay, now I'm happy, right? Because W is also an eigenvector. So what is AW? Well, that's mu times W transpose V. But again, by distributing this, this is mu times W transpose V.
Isn't it lambda?
No, there is no lambda here. There is mu. This is the important thing. So W is an eigen.
Oh, I got it.
Mu and lambda. W is an eigen vector with eigenvalue mu. This is what I'm using. There's a mu in one place and a lambda in the other place. Is that okay?
Yeah, I got it. Thank you.
Okay, good. But now this is exactly the point, right? If these two things are equal, well, what does this imply? This implies that lambda minus mu times W transpose V is equal to 0. This thing is not 0 because they're distinct. So this has to be 0. That's the proof, right? That means W is orthogonal to V. Okay, so the explanation for why symmetry implies orthogonality is actually very clear. It's this basically like one line proof. You just calculate W transpose AV in two different ways, and they have to be the same, right?
Do all real do all like real symmetric matrices have distinct eigenvalues?
No, they don't. They don't necessarily have distinct eigenvalues. So this is why the theorem is. This is why we haven't proven the full theorem, because we didn't prove that there are n linearly independent eigenvectors, right? We just proved that whenever there are two eigenvectors from distinct eigenvalues, they're orthogonal. So.
So they said all of the eigenvalues are real.
Are real, yeah, but some of them might be the same.
Okay, so they can be complex value, which means
they cannot be complex, yeah. So this is a kind of a magical thing that if you have a symmetric matrix, the eigenvalues are always real.
Then can just a quick question, can complex eigenvectors be orthonormal or orthogonal?
We haven't defined what that means. So there is a notion of orthogonality for complex vectors, but not in this class.
Okay.
Yep. Orthogonality is something about real vectors. That's why it's important everything is real. We didn't define what it means for complex.
But they do exist.
Yeah, the concept exists.
Okay.
Mm-hmm.
Just different.
Yeah.
All right, thanks.
Okay, so that proves one piece of this theorem. Okay. So maybe I won't add the remark. I already wrote on the previous page that the eigenvalues may not be distinct. Okay. So maybe so how was orthogonality used here? So this is something I only learned in grad school, which is what does transpose really mean? And this is the key property of transpose. That is used in all interesting places where transpose is used. The key property is that W dot product AV is equal to A transpose W dot product V. Right? So that's what we used in this line. Right? That's where, that's where the transpose was applied, and then symmetry was applied in the next step. But really, if you're wondering what is the meaning of transpose, Well, this is actually how it's defined when you take like graduate math or whatever. It's defined as the, the operation that has this property, that when you move it across the dot product, you get that operator. Okay. Okay. Yes. So somebody's saying if they're zero, so then they have to be orthogonal. That is correct. That's how the proof is. Okay. So that's proof of a small part of the spectral theorem. Let me now explain the meaning of the theorem, right? Or first, let me show you an example. Here's an example. Let's consider this simple symmetric matrix. Okay. What's its characteristic polynomial? Well, let's just compute it. So this is 1 minus lambda squared minus 1, which is just lambda squared minus 2 lambda, which is lambda times lambda minus 2. Right? So this indeed has two eigenvalues, which are 0, or actually let's sort them this way, which are 2 and 0. Okay. And you can compute the corresponding eigenvector, which I mean, I don't want to do the row reduction right now, but let's just write down what they are. This is something you're familiar with. Eigenvectors. So the first eigenvector is this, and I'm normalizing it to be a unit vector, right? That's why I've introduced this funny square root 2, just so it's a unit vector. And the second eigenvector, if you do the row reduction, turns out to be this. Okay, and indeed, their dot product is 0, as it should be according to the theorem, right? Okay. So that's an example. Now, what does this mean? Well, there are two interpretations of the spectral theorem. So now what I can do is I can make a diagonal matrix P out of these eigenvectors. Right? And okay, this is an orthogonal matrix. And if you really think about what this is the matrix of rotation by pi over 4 radians clockwise. Okay, if you just plot what this is, that's what this is. So now orthogonal diagonalizability tells me that A is equal to P D P transpose. So if P is rotation by pi by 4 clockwise, what's P transpose? What's the meaning of P transpose?
Counterclockwise.
Counterclockwise. How do I know that was a rotation? That was one of the examples like before the first midterm. So I went back to that example. I mean, I didn't do the calculation right now, but you can just plot. I mean, it requires a little bit of trigonometry, but you can verify that. So yeah. So again, what is P transpose? Well, it's the same as P inverse, which is rotation by pi by 4 counterclockwise, the other direction. Right? Oh, and I knew it was this rotation because cosine pi over 4 is 1 over square root 2. Okay. So what this is telling me is that this matrix A, what it's really doing, it gives me a meaning, which I'll call meaning number 1, because there's also meaning number 2. Meaning number 1 is that this literally corresponds to rotate by pi by 4 counterclockwise. I mean, I'm writing it in reverse. And then this is just scaling, right? So 2, 0, and then rotate by pi by 4 clockwise. So I'm writing, it means I can write A as rotation, scaling of the coordinates, and then the inverse rotation. So let's just visualize this. So let's just visualize it on two vectors, E1 and E2. So now what happens when you hit this with, you're going to do PDP transpose. So first you hit it with P. Well, that's supposed to be rotation by pi by 4 clockwise, right? Oh, I'm sorry, I got it backwards. Whoops. This is clockwise and this is counterclockwise. Right? P transpose is counterclockwise. Okay, so let's now, so what does this look like? Well, when you rotate something counterclockwise, it now looks like this. So this is P transpose E1, this is P transpose E2. You rotate. Now the next step is you're going to hit this with D. Now what does D do? Well, it kills the second coordinate and stretches the first coordinate by 2. So actually, when you plot what this is going to look like, you're going to get something that looks like this, right? So it's going to be some stretched version of just the x coordinates of these vectors. So this is going to be dP transpose E1, and this is going to be dP transpose E2, right? Because I'm literally hitting these with a diagonal matrix that kills the y coordinate. And now I hit this with the reverse rotation, P. And that's going to now rotate this whole picture clockwise. So what I'm going to get is actually these vectors like this. I mean, they should be long, but this is going to be AE1, AE2. And indeed, if you look at these two vectors, that's what those are, right? So 1, -1, and -1, 1. Okay? So that's what this theorem is saying, that every symmetric matrix is rotation, scaling, reverse rotation. It's a very beautiful characterization of every symmetric matrix.
Wait, the eigenvalue is 0. I'm just a bit confused. Why won't the E2 disappear? Like,
well, no, because I'm applying. Remember, I'm applying D to P transpose E2. Right?
Oh yeah.
I'm not applying it to E2, right? So it gets flattened like this, but it doesn't disappear.
Oh, okay.
Yep. So the summary, which is true for every matrix, every symmetric matrix is, can be written in this way: rotate, diagonal scale, and then rotate back. Okay, so that's a very amazing characterization. And symmetric matrices really come up all the time. I mean, I spent most of my mathematical life looking at symmetric matrices. So this is not some very special class of matrices that's not important. It's really important. So that's the first meaning of the theorem. Let me now explain the second meaning of the theorem. There are two different ways to interpret it, basically. For meaning number 2, I actually need to introduce a new way of thinking about matrix multiplication. So I think we did the high school way, and then we did the college way. We did linear transformations. But there's something which I learned in grad school, which is the grad school way of thinking about matrix multiplication, which for some reason I didn't learn until grad school. And it's the following. Suppose you have a matrix A that's M by P. So that means it has P columns, which live in Rm. And now suppose you have another matrix B that's P by N. And this has now P rows, right? So B1 transpose all the way up to BP transpose, where these BPs live in Rn. Okay. So then the product, so this is a bit funny, right? You're used to looking at the rows of the first term and the columns of the second term. But now we're looking at the columns of the first term and the rows of the second term. Then you can check that this is equal to A1 B1 transpose plus A2 B2 transpose all the way up to AP BP. Okay. So you can check this. I mean, each of this makes sense, right? Each of these things is an m by n matrix, right? It's an m by 1 matrix times a 1 by n matrix. So it's an m by n matrix. And each of these is a rank 1 matrix because, well, every column is a multiple of A1. So this is something you can algebraically verify, but this is yet another way to think about matrix multiplication. What does this imply about the spectral theorem? Well, if A is equal to PDP transpose, well, D is this diagonal matrix containing the eigenvalues. P is a matrix containing the eigenvectors, which are now an orthonormal basis, right? Well, then what does it look like when you multiply it out this way? Well, it looks like U1 up to UN times the diagonal matrix D times the transpose. And so if you just work this, if you apply this new way of looking at matrix multiplication here, you get that this is literally lambda 1 U1 U1 transpose plus lambda 2 U2 U2 transpose plus all the way up to lambda n UN UN transpose. Okay. So this is a different way to write this orthogonal diagonalization as a sum instead of a product. Now, what does this sum mean? Well, what does a matrix like this mean? So what does that matrix have an interpretation? Anybody know what that matrix means? Use a unit vector. Oh. Projection, exactly, right? So this is the matrix of the projection onto the span of UI. Right? Because when you multiply this by x, yeah, this is only for symmetric matrix, correct? If you going back to chapter 6, you can see that this is the matrix of a one-dimensional projection. So what is this theorem saying? Or what is this meaning? What is this way of looking at it saying? Well, it's saying any symmetric matrix is a weighted sum of projections where the weights are the eigenvalues. So maybe I'll write this in blue since that's what I used for the other one. Onto the eigenvectors. And the weights are the eigenvalues. So that's the second meaning. So let's again go back to our example, or let me write it on a new page. We had a matrix A that was 1, 1, minus 1. This was written as PDP transpose, but the eigenvalues were 2 and 0. So this is 2 times mean, the eigenvectors, I guess we call them V, right? Yeah. So 2v1 plus 0, which is the second eigenvalue, times v2. So what is the geometric meaning of this? Well, so remember, v1 is this vector, I think 1 over root 2 minus 1 over root 2. And v2 is this vector 1 over root 2. So let's again draw the picture of what happens to the standard basis vectors. So again, we started off with some E1 and E2. Okay. But now there are these eigenvectors, right? There are these two eigenvectors. So V1 looks like this, or sorry, V1 looks like this, and its span looks like this, and V2 looks like this. So according to this interpretation of the spectral theorem, what should be happening is that we should be computing the projections of these vectors onto both eigenspaces and stretching them by the eigenvalue. Now this one corresponds to lambda 2 equals 0. So whatever gets projected there will not be stretched at all. What gets projected down here will be stretched by a factor of 2, right? So you'll have this. So this vector you will literally get will be twice the projection onto the span of V1 of E1. And here you'll get twice the projection onto the span of V1 E2. And that's the same as what we got in the other meaning, right? It should be the same. It's the same answer, right? AE1, AE2. But it's a different way of interpreting it, right? That every symmetric matrix is just a weighted sum of projections. And the projections are onto the eigenvectors, which are orthogonal. Okay, so any questions about this?
So why don't you like project V2 onto E1 and
E2? Well, because that's not what the theorem says, right? So the theorem says that the matrix is equal to a sum of projections onto the eigenspaces, right? So look at this red box. The things here are not standard basis vectors, they're eigenvectors, right? So these are eigenvectors. That's, I mean, that's just not what the theorem says. Does that answer your question?
Okay, so like, so I have another question. Like, can I modify the question about like why don't you like project your E1 onto the V vector?
Onto V2, you mean?
Yes.
Okay. So you do project it, or you actually do project it. You do, okay? But then it gets multiplied by 0. So you just get 0. Does that make sense? So okay, so I mean it's okay. So that means A E1 equals twice V1 transpose E1 plus 0 times V2 transpose E1, right? But now this term just goes away because there's a 0 in front of it. And so this is why you get twice the projection onto V1. And the other one goes away. If the eigenvalue was not 0, you would get something there. Does that answer your question?
Yes. Okay. Thank you.
Okay. Okay. So that's called the spectral theorem. So, I mean, this really is my favorite theorem. And I mean, if you do physics, I mean, I've taken courses in physics where people have actually referred to this as the fundamental theorem of physics. And the reason for that is that pretty much all of quantum mechanics is based on this theorem. Anyway, I'm sure you'll come across it in life, but now I want to tell you about how you can use this to understand rectangular matrices. I see. So the question is that different from projection of 2E1? No, it's not, because projections are linear. But the meaning is that the eigenvalue sits in front of the projection. So, right. So the question was, is 2 times the projection the same as the projection of twice the vector? No, it's not, because projection is a linear transformation. Any other question? Okay. So now I want to move on to rectangular matrices. Okay. So what's the goal? Well, given some matrix A that's m by n. So remember, an m by n matrix is a linear transformation from Rn to Rm. You want to find a pair of bases. Let's say B of Rn of the domain and C of Rm, such that when you write this in these bases is as simple as possible. Again, that will mean something like diagonal. Same goal that we started chapter 5 with. Okay, so there are many ways to motivate this. This is probably the most useful theorem in this course. I mean, every area of, certainly applied math and most sciences uses this theorem in some way. I should mention that in statistics, this is called principal component analysis. In quantum mechanics, it's called the Schmidt decomposition. Okay, so how do we find a pair? It says find a pair of bases. Okay, so how are we going to do this? Well, the perspective I'm going to take is I'm going to go back to our last theorem I proved before the lecture, which was the fundamental theorem of linear algebra. So recall fundamental theorem of linear algebra, which says that if you have any m by n matrix, then the row space of A is isomorphic to the column space of A. And the isomorphism is just the multiplication by A. So in particular, this implies the row rank, that they have the same dimension, the rank of A is equal to rank of A transpose, and all these other amazing stuff. Let me draw the picture of this just to remind you in case you forgot. The picture is that if you have an m by n matrix, then you can decompose Rn into the row space of A and its orthogonal complement, the null space of A. And then you can decompose Rm into the column space of A and its orthogonal complement, which is actually just a null space of A transpose. And now you have this sort of beautiful thing happen, which is, well, so this is 0, 0 gets mapped to 0. This whole null space actually gets mapped to 0. And then up here, the row space gets mapped to the column space, and this is an isomorphism. And that's just multiplication by A. Okay. So by the way, so let's suppose the matrix has rank K. Now, one consequence of this is that if you take any basis for the row space, it's going to get mapped to a basis for the column space. So here's a consequence. You take any basis, let's call it V1 to Vk. And let's say you hit it with A, then AV1 through AVK. Well, remember, multiplication by A is an isomorphism on the row space, right? So AV1 through AVK is also going to be a basis. Okay. So that means, any basis that's sitting in the row space of K vectors, when you hit it with A, you get some basis of the column space. But now I'm going to ask a sort of more subtle question, which is, what if you take an orthonormal basis of the row space? So let's say you take an orthonormal basis of the row space. So you take some vectors that look like this. So V1, that's an orthonormal basis of the row space, right? So maybe I'll make this K just to indicate that it's a row space. If you hit it with A, are you going to get an orthonormal basis? So does isomorphism preserve orthonormal basis?
Yes.
Does isomorphism preserve orthonormal basis? Is that the question?
Yeah.
No, it does not.
So this is a subtle point. This was actually question number true false final question on the midterm. Isomorphism, things like change of coordinates don't preserve the dot product. So in general, it's not true. If you start with an orthonormal basis of the row space and hit it with A, you do not get an orthonormal basis of the column space. Right? Because A can do all sorts of funny things to the dot product, basically. What I'm going to show you is that there's actually a special choice of orthonormal basis, which does get mapped to an orthonormal basis of the column space. Okay. So there is a special orthonormal basis, let's say V1 through VK of the row space, such that if you look at the images, this is an orthogonal basis of the column space. Okay, the lengths might get changed. We'll talk about that in a moment. And that's what singular value decomposition is all about. So there is some magic choice of basis so that when you hit this V1 through VK by A, on the other side, you still get an orthonormal basis. An orthogonal basis, sorry. And now I'm going to show you how to find that. Okay. So any questions about the setup?
Can you go back to the last slide real quick?
Sure.
Okay.
Yep. Okay, so what's the idea here? AVI is just orthogonal, not orthonormal yet. But we will make it orthonormal by normalizing it. Okay, but that's already pretty good, right? So if you take a general or orthonormal basis, it'll get mapped to something that's not even orthogonal. Okay, so here's the slick idea. So this is a short proof, but it's kind of magical. Here's the idea. So consider the matrix A transpose A. So that's an n by n matrix. It's also symmetric because A transpose A transpose equals, okay, A transpose. We just discussed symmetric matrices, right? The spectral theorem applies. So what does that mean? Well, it means you have n real eigenvalues. Okay. You have n real eigenvalues. Actually, the eigenvalues are also non-negative. Okay, so I'm just going to prove this in a separate box here. The proof is very straightforward. Well, suppose A transpose AX equals lambda X. Just hit it with X transpose on both sides, right? But then that means lambda times norm of X squared equals norm of AX squared, because, right, the first quantity is norm of AX squared. But then this implies lambda is, might be 0, but it cannot be negative. So it's a short proof. So actually, you even strengthen this. You get these numbers that are actually non-negative. So A is any rectangular matrix. You look at A transpose A, you get a symmetric matrix with non-negative eigenvalues. How many of those eigenvalues are non-zero, by the way? Anybody have any thoughts? Somebody said n minus 1 at least. Why do you say that? They're unique. They're not unique. Okay. So somebody said that these eigenvalues, you know, there must be at least n minus 1 non-zero ones because they're unique, but they're not unique. These are less than or equal to, right? So may be equal. They may all be equal. The next suggestion is, do they correspond to the number of linearly independent columns k? That is correct. Here's fact number 2. Fact number 2 is that, I mean, okay, there are a number of ways to prove this. What's the easiest way? Well, let's say you, okay, fact number 2 is that the number of non-zero lambda I is equal to the rank of A, which is equal to K. Okay, why is that? So somebody suggested that. There are many ways of proving this, but any thoughts on how to prove this? Row reduce? That's not such a good idea because row reduction messes up the eigenvalues. Remember, row reduction preserves the rank, but it messes up the eigenvalues. So that's actually not such a good idea.
Could perhaps looking at how could we start looking at how let's see, how the linear dependence of the columns of A affect things, or no? I'm not. No, I'm
Okay,
thinking about something different.
Okay, yeah, what you're saying might work, but many people have suggested one very correct answer. And the answer is that, well, you have to use that the null space of A transpose A is equal to the null space of A. This you can prove, for example, by thinking about least squares or many other ways to prove this. But then this implies that the rank of A transpose A is equal to the rank of A by rank nullity, right? And then somebody else added the second important comment, which is that the nullity of A transpose A is just the multiplicity of the 0 eigenvalues. So in this picture here, the number of 0 eigenvalues, this is the nullity of A, right? The eigenspace for, this is the eigenspace for all the 0 eigenvalues. So this must be the rank. Okay, there are many ways to prove this. It's a nice exercise if you want to refresh your existing knowledge, but that's one of them. Apply rank nullity Let's look at the zero eigenspace and use this fact that the nullity of A transpose A is the same as the nullity of A. So this is a general fact about symmetric matrices, by the way, that the number of non-zero eigenvalues is equal to the rank. So maybe I'll just add this here since it's an important fact. So by number, I mean with multiplicity, right? But since symmetric matrices are diagonalizable, geometric multiplicity is always algebraic multiplicity. These are some, little facts that I used. Let's go back to the proof. There's a little bit of a diversion, but let's go back to the proof. So we looked at A transpose A. It has k non-zero eigenvalues, and the rest are 0. Okay. So now,
Oh wait, on the far left side, it's the for the eigenvalues are non-negative thing. It says ax squared. Should it be ATA instead?
no, it's norm of ax squared. So here I'm using that. I reverse the equation, right? Maybe I'll write it this way. Maybe it'll be clearer. The left-hand side is literally the norm of ax squared because it's ax transpose ax.
Okay.
The right-hand side is lambda times norm of.
Oh, okay.
Okay, good. So now, well, what does that mean? So, so the first thing I want to observe is that the corresponding eigenvectors, so they're k non-zero ones, right? So these have some corresponding eigenvectors v1 through vk. These are correspond to the non-zero, and then there are some other eigenvectors. Okay. And these are actually orthonormal by the spectral theorem again. The eigenvectors of symmetric matrices are always orthonormal, right? Okay. But now, okay, so what's the first thing I want to say? Yeah, so all of these things actually lie in the orthogonal complement of the null space, right? Because all of these things lie in the null space, of A transpose A, which is the same as a null space. Right? The zero eigenvectors are in the null space, that's just what it means. And the non-zero eigenvectors are in the orthogonal complement of the null space, otherwise known as the row space. But now I have k orthonormal vectors in the row space. That means that these are an orthonormal basis for the row space. So v1 through vk are an orthonormal basis for the row space. This is the key fact I wanted to derive through all this reasoning. There are probably other ways to derive it, but this was one of them. So any questions about that fact? So far, I've just derived that if you form A transpose A, look at the eigenvectors corresponding to non-zero eigenvalues, you get an orthonormal basis for the row space. Notice that this is a completely different way to get an orthonormal basis for a row space from what we studied before the midterm.
I have another question about like null of ATA is equal to null of A.
What about it?
So like, for example, if something is not in the null space of A, so AX will not be 0, then how do you ensure that the product that you're coming out of AX, when you plug it in into AT, will not turn into 0?
Yeah, so this requires a proof, which I don't want to do right now, but you can treat it as a little homework exercise. But you can prove via least squares. That's the easiest way to prove it.
Mhm.
So I won't cover the proof right now, but
Okay.
this is a fact that you can convince yourself of. Thinking about least squares is the easiest way.
Okay.
Thinking about uniqueness for least squares. Okay, so there's a lot going on here, and please ask if you have questions, because this is probably the most intricate thing in the linear algebra part of this course. Okay, so we have an orthonormal basis for row space of A. So now we have V1 through Vk sitting over here. Now the
Sorry, I have a
punchline,
question.
yes.
So you said that when we find the eigenvectors of this row A that they're orthonormal, but I thought that we had only proved that they're orthogonal.
No, so okay, so eigenvectors, remember, eigenvectors, they can, if you scale an eigenvector, you get another eigenvector, right?
Mm-hmm.
So once you get orthogonal eigenvectors, you can just scale them to be unit vectors and they'll be orthonormal.
Okay.
So the spectral theorem, going back here, actually says there's an orthonormal basis of eigenvectors, right?
Mm-hmm.
And in this setting, there's no difficulty because you just scale them.
Okay, thank you.
Okay, so now we have these VKs. Now, as I said I was going to tell you that there was a special basis, right? Well, this is the special basis. So what's the punchline? The punchline is when you hit these with A, they're still orthogonal. Okay, so let's do this on the next page. The punchline is consider the vectors V1, AV1 through AVK. Now these definitely live in the column space of A, right? By definition, they're A times some vector. These are also orthogonal. Okay, now why is that? Well, the reason is, let's pick two different of these vectors, right? So let's look at A Vi dot A Vj. Well, what is that? Again, it's this trick with transpose, right? So that's Vi transpose A transpose times A times Vj, right? But aha, what's special about these vectors? They're eigenvectors of A transpose A, right? That's how I chose them. So actually, this is just Vi transpose. I just view this as one term, and that's just lambda j Vj. By the way, this lambda j is not 0, right? Because I chose these to be the non-zero eigenvectors. So this is now, I mean, that's not actually being used here, but this is Vi transpose Vj, which is 0 by the spectral theorem, right? Because A transpose A was symmetric, Vi and Vj were already orthogonal. So this is for I not equal to j. And for I equals j, it's equal to this. But remember, lambda j is not 0. Right? That's how I chose these eigenvalues. I've singled out the positive eigenvalues, of which there are k, where k is the rank. So that's great, right? That actually proves what I wrote here, that these AVIs are orthogonal. It comes from the eigenvector equation. So this is all by the spectral theorem. Or, because the VI are orthogonal. Okay? So that's it. Somehow by finding an orthonormal basis of eigenvectors of A transpose A, I found this special basis, orthonormal basis of the row space that gets mapped to an orthogonal basis of the column space. So to make it orthonormal, I just need to scale them, right? To make orthonormal, I'm going to define some new vectors U1 to be just this vector, but now to be a unit vector. Okay, and these scaling factors are really important. So sigma, these are called the singular values. And well, how do you compute them? There are many ways to compute them. One is you just note that the square of the ith singular value is norm of A VI squared, which is VI transpose A transpose A VI, which is, since VI is an eigenvector, just lambda I. So these numbers are just the square roots of the eigenvalues of A. Okay. So let me now summarize what we achieved. Are these non-zero? Yes, these are non-zero. These are all non-zero. Because remember, K was chosen so that these are not zero.
I have another question about so for example, if a matrix is like symmetric, did it mean like for any kind of so if a matrix is symmetric, that means that all of its eigenbases is orthogonal.
Yeah.
Which can, and is that means that all of these bases can be used as the basis for singular value
okay, so it's not all of its eigenbases are orthogonal. You could choose one that's not, but for a symmetric matrix, there is an orthogonal eigenbasis, and there may be many of them. You're wondering what happens if there's multiplicity, right? Maybe you're wondering, maybe there are many choices for these V1 through Vk, right? Is that what you're asking?
Yeah, kind of like so.
Yeah, any choice will be fine. So, I mean, does that answer your question? So, question.
Yeah. So is like you don't have like a specific singular value decomposition for a matrix?
Yeah, it's not unique. I mean, there are ways to add constraints to make it unique, but what I'm describing is not unique.
Okay.
Okay. So what's the summary? Well, the summary is we found, what did we do? So you orthogonally diagonalize A transpose A, and you get non-zero eigenvectors V1 through Vk, or non-zero eigenvalue. Which are all strictly positive, right? And then the claim is define these new vectors ui to be A vi normalized otherwise known as AVI divided by the sigma I for sigma I equals square root lambda I. Then you have two properties. Then V1 through Vk are an orthonormal basis for the row space. U1 through UK are an orthonormal basis for the column space. And you have the relation AVI equals sigma I UI, where I goes to 1. This is the thing that takes a substitute of the eigenvector equation. The VIs get mapped to the UIs, and the scaling factors are these singular values. Now, why is this called a decomposition? Well, let's write it in matrix notation. In matrix notation, this is saying that A, when you multiply A, which is an M by N matrix, by a matrix whose columns are the V's. So this is a N by K matrix. Remember, A is rank K, right? Then this is equal to the U's, but multiplied by sigma I's. So again, in matrix notation, that would be U1 through UK. What dimensions is that matrix? Anybody know? Well, it's a matrix, so it has to have two dimensions.
So this one has to be M by K, right?
M by K times a diagonal matrix that contains the singular values. I mean, okay, let me rewrite this since it's quite important. So this is M by K, and this is K by K. Okay, so one way of writing this is AV equals U sigma, where you have the following properties. Sigma is diagonal, and both V and U have orthonormal columns. In other words, V transpose V equals identity, and U transpose U equals identity. So this is how you write the same information in matrix notation. Okay. I'm literally writing what's written in down here in matrix notation, that these are orthonormal bases and one gets mapped to the other. Okay. And now the thing that's normally called the singular value decomposition is just a slightly different way of writing this equation.
Well, you're writing it in the ways that you are because you can't simply divide both, quote unquote divide. Well, you can't find the inverse of the N by T matrix, correct? That's
yeah, that's right. But what you can do is you can multiply on both sides by V transpose, right? So you get A VV transpose equals U sigma phi transpose, right? You can do that, right?
yes.
But what's VV transpose?
That's going to be identity, N by N identity matrix.
No.
Wait.
So,
VV transpose, correct?
Yeah, V transpose V is an identity matrix.
Oh, okay.
V transpose V is a K by K identity matrix. VV transpose is a projection matrix
Oh,
onto the row space. Okay, which just means it's a projection orthogonal to the null space. So it doesn't actually do anything. Okay, I mean, there's a lot going on here, and you have to. I'm not expecting everybody to follow all these details as we're doing it right now. I agree, it's a lot. But it really does fit in these 2 pages. It's a 2 pages that uses like everything we learned in this course. But this is what's called the singular value decomposition, otherwise called the truncated SVD. And the reason it's truncated, there's something called a full SVD, which I won't have time to discuss today. But what's going on here is that U and V are matrices with orthonormal columns. Sigma is a K by K matrix. So again, using the grad school definition of matrix vector multiplication, it means you've decomposed A as a sum of rank 1 matrices that look like this. Okay, so this is what's normally called the SVD. What it's saying is any rank, it's saying a whole bunch of things. I mean, sort of the ultimate fact about it's like the ones, if you know this, you know everything else about the matrix. I see, there's a question. Why doesn't VV transpose do anything to A? I'll answer that on the next slide. It gives you a base, it gives you an orthonormal basis for the row space that gets mapped to the column space. It gives you this decomposition of the matrix as a sum of rank 1 matrices, which have this orthogonality property, which is what's important in many applications. It solves a whole bunch of different optimization problems, which maybe I'll say a little bit about next time. So I won't be able to finish SVD this time. But okay, let me end by answering this question and running this on an example, because a lot of stuff happened, right? So first, the question. I'll tell you the application next time. V or V transpose equal the projection onto the row space of it. That's the question, right? So first of all, the reason this is the projection on the row space is that the VIs were, an orthonormal basis for the row space, and a matrix of an orthogonal projection looks like this, right? Well, the answer, let's just check, right? Suppose X is in Rn. Let's decompose X as its projection onto the row space plus the projection onto the null space. I can do that by the unique decomposition theorem, right? Now, what's AVV transpose X? Well, or maybe let's just start it. Let's start it with AX. What's AX? Well, it's A times the projection onto the row space of AX plus A times the projection onto the null space of AX. Is that okay? Everybody okay with that? Okay. Can somebody say yes or no?
Yes.
Okay. Okay. Now the first term is AVV transpose X. What's the second term? Zero, right? This thing is always in the null space. So A kills everything in null space, plus 0. That's the proof. You can write multiply by the projection on the row space and nothing happens. Okay. Finally, let me end with a short numerical example just to try to consolidate these concepts because a lot of stuff happened here. So here's the numerical example. Numerical example is find the SVD of the following matrix. This is just an example from the book. I just want to highlight the algorithm. First step is form A transpose A. So A transpose A in this case is a 2 by 2 matrix, which if you work it out is this. And as you can see, this is just a scalar multiple of the matrix in the first example. So it has eigenvalues 18 and 0. So this is 9 times that matrix. And eigenvectors those are the eigenvalues and eigenvectors of this matrix. Now I need to find the UIs, right? So now I'm going to compute A V1. So let's do the calculation. AV1 turns out to be, remember, this is now a 3 by 3 vector. This is 2 over root 2 minus 4 over root 2, 4 over root 2. AV2 is the vector, well, AV2 is actually just the vector 0, 0, 0. Should I be surprised by that? Why is AV2 0? Because it's a 0 eigenvalue, right? 18 corresponds to this, and lambda equals 0 corresponds to this. So I should not be surprised. So the only one that's going to form a basis for the column space is U1, which is AV1 divided by sigma 1. So let me just compute sigma 1. So so lambda 1 equals 18, lambda 2 equals 0, sigma 1 equals square root 18, which is 3 square root 2. So this is going to be AV1 divided by 3 square root 2, which is turned out to be a third minus 2/3 and 2/3. Okay. So what's this SVD that I get? I get that A is equal to U, so this matrix, sigma. So sigma is just a 1 by 1 matrix containing 3 root 2. And now V transpose is just going to be so U sigma V transpose. Okay, so that's the singular value decomposition of that matrix. It effectively factorized the matrix, right, in a way that made it very clear that it's rank 1. Now the book has something also called full SVD. And this is not really more complicated. In this case, I mean, I won't talk about it now, but there are some homework problems assigned about it. Please just read up on it and do them. It's the real interesting part is what I did in the lecture. And I'll tell you a really cool application of this next time. Anyway, thanks.